Good day, everyone. Okay, when we start the second part of the morning session, and we request Dr. Maksym Titov will come in to continue with his talk about gaseous detector.
Okay, thank you very much. Thank you very much for So today we will make a trip to the second lecture of gaseous detectors, and actually, thanks to Danielle, it was extended to 3 lectures. And this is very nice, so that you get from different perspectives the gaseous detectors. And I think one of the points which Daniel pointed out very correctly, I was saying that many things with gaseous detector is somehow black magic. He pointed to chemistry, which I fully agree. But the key element, as you would be growing as a detector experimentalist, and many of you already in the big experiment or will come in the big experiments, you need to develop yourself as a detector physicist, understanding the basic processes in detector, whether it's gaseous, silicon. Because now when you come to the big experiments like LHC, you're usually charged with some work on engineering, construction, detector, etc. And you might have less time by the pressure of big experiment to understand the basic physics of the processes. This is extremely important because in general, LHC detector is successful, but there was some failures which could be recovered here and there. And these failures comes very often because of some crucial selection in the last stage of something in detector construction, and maybe not guided so much by detector physicists, by the project management who needs to be accomplished on time. And then this results in a failure, which has a far-going consequences. And this is what you develop from black magic to chemistry, you develop experience. And this experience comes, first of all, with a good knowledge of the basic physics of the detector. And this is what you need to learn. And then, of course, by building more and more detector. So I warn you, and I argue that whenever you come to big experiments, devote part of your time to understand the basic processes of the detector. And there are many things which helps. So I know it was a heavy lectures yesterday, and they already uploaded. There is 100 slides, but I hope that if you look on these slides on gaseous detector, it will serve you like a guidelines, and you using them learn more. I mean, because they are heavy transparencies, but this is what I try to summarize you the basic of detector physics of gaseous detector. So we discussed yesterday about how ionization is produced in gas. We discussed yesterday how it drifts to the electrodes. We discussed yesterday how we select the gas mixtures, etc. We already at the point of how we generate the signal. But before we generate the signal, let me point out, we discussed how we transport electrons, okay, to the anode. But ions, they play also important role. Contrary to electrons, they are not heated up. Okay, because they're very heavy, so they're not accelerating. They drift more or less uniformly, and their drift velocity is pretty much uniform. But still, there was a major point which was discovered only recently, what Daniel was telling you. Always it was considered that its ions is the lowest ionization potential that take a charge from other ions and read to the cathode. And recent simulation improvements showed up that this is not the case. This is not true anymore. So it was understood that this experimental data suggests, for example, that if you take an argon CO2 mixture, then naively exchanging, you consider argon ion exchanges with CO2, which has a lower potential, and this ion drifts, for example, to cathode. But this is not true anymore, because it looks like there are processes which creating a cluster ions, more complicated ones, like CO2 plus times CO2. This is the ions which drifts in the detector and the cathode. And this is the ions will be much slower. And what Daniel was telling you, the signal generated in the chamber is related to the ion drift. So basically, the slower they drift, the change of the signal and the amplitude signal will be modified. So this is another very important point. And this is actually came with the simulation improvements. And again, I mentioned to you yesterday about the things, but simulation has changed significantly since 80s, and many things has improved. And now what you do in simulation, you don't calculate some equation, but you really do microscopic tracking step by step. Okay, so you just move by few tenths of microns and you calculate all the probability processes cross-section with the molecules. So many things has improved. But this is what gives you a summary of the simulation which exists in gaseous detector. So you have two programs, heat and degrade, which allows you to do some energy loss, what we discussed yesterday, and also simulate the cluster size distribution, remember from yesterday. You have also the program SMACBOLS, which allows you to simulate electron transport properties, drift diffusion, multiplication attachment. We talked also about that some electron can be lost. You have some of the electric field map. This is what you have. And on top of everything, you have a Garfield, which have fields, drift properties, generation of signal after amplification, and everything interfaced above. Some of this program is commercial, but I would like to draw your attention in particular one program which was developed in India by Supratik and his team, nearly exact boundary element method, which allows to solve some field equations based on the Green function-based solver. And basically, there are many, it was actually the first note of the RD51 collaboration about what you are saying and also published. And there are many other things, and this is currently updated in SAPD. It allows to solve many, we wouldn't go in details, electric field structure, and contrary, for example, to console or ANSYS, it doesn't require license. And of course, Garfield package, which combines everything, and Garfield can be also interfaced with GEANT. You cannot simulate gaseous detector precisely with GEANT, okay? Not all of the things. The simulation improved, but if you really would like to simulate gaseous detector, you need to use Garfield, which you can interface all other programs and simulate precisely properties of the gases. Okay, so we moved electrons towards the anode wire, and then but it's only 100 electrons per centimeter, you remember, the particle path. This 100 electrons reaches the cylindrical field around the wire, and then in between the two collisions, the field becomes enough for that each electron can produce another electron-ion pair. This is what is called gas amplification. So basically, you have an avalanche effect, which starts typically the wire diameter of 20 microns, 50 micron, and typically at the distance of 50 micron per wire, in between the two collisions, electron gain enough energy to produce electron-ion pair. So there is a multiple multiplication of the drifting charge. And this is what called gas multiplication. Is it clear? Yes? So, and this is the main point. So you have 100 electrons, then you have a multiplication factor 10 to the 4. It means that every original electrons generate your extra 10 to the 4 pairs, and then this is your total charge. And 10 to the 2 times 10 to the 4, 10 to the 6, this is much, much better than what is required by your electronics. So you get the signal on the wire. Okay, and this is a different stages. So the electron comes, it starts to, and then electrons are quickly absorbed on the anode, and ions slowly drift to the cathode. And this is what generates a measurable signal on the wire. And you can describe it by the so-called the theory. You describe it when you hear Townsend coefficient. This is exactly the coefficient which allows you to determine, and determined by the excitation and ionization cross sections, this amplification coefficient. You usually measure it as a function of electric field. This is clear. And there is no fundamental expression for it. While in the simulation program, you can get now very precisely by microscopic tracking the correct Townsend coefficient. This wasn't the case 20 years. You cannot simulate probabilities again. Now you can do this much more precisely. But it can be measured for every mixture, and here you can see the Townsend coefficients for different fields, just for you to remember the Townsend coefficient. And then this defines you as several processes which exist in gaseous detector. Here you can see the number of electron ion collected as a function of the voltage. This is a very, very old plot, but it's very nicely since 70s, summarize everything. So you have several modes of operation of gaseous detector. First of all, ionization mode. So you produce electron-ion pairs. The field is not enough for multiplication close to anode, but you collect all the charge, you measure the current. This is called the ionization mode, okay? So first, you just collect all the charge. Then, when most of the counters work, proportional mode. So what we discussed, you start multiplication of the original ionization by proportional, because in this area, the total signal is proportional to the number of electron-ion pairs. Clear? So basically, you multiply if you have originally 10 to the 2 electron, you multiply by 10 to the 4, you get to the 10 to the 6. If you have 10 electron ion pairs, you multiply 10 to the 4, your signal would be 10 to the 5. Why it is important? Because in this mode, you know the energy which was originally deposited, and through this try to identify and to connect it to the energy loss, which allows you particle identification. This happens at the gains 10 to the 3, 10 to the 4. Then there is a so-called later on, so you can discriminate, for example, in this mode, proportional alpha from beta particle. Then there is a semi-proportional region where the charge already not proportional to the original charge. You certainly get over the threshold, but it's not directly proportional. Then you go to more advanced mode, limits of regional limited proportionality saturated streamers, and 10 to the 6, 10 to the 7. In these cases, there is a lot of the photon activity, so there is a lot of photon excitation, and you need more and more heavier quenchers, as we discussed now, to absorb this photon and to stop the discharge which is being developed. But you lose the attractiveness of this. And then you go to the mode of Geiger mode, Geiger counter, like first Geiger counter was doing, so particle passes and then you have a discharge propagating through all the wires. You were going with the time in this direction using gas detectors. Why? Because it related to the best way you do in the proportional mode with the lowest gas gain. But it became possible with the development less and less noisy electronics, okay? So this is why from 70s to 80s to 90s to 2000, you were moving along this curve while more precise electronics with less noisy electronics was appearing. Clear? Okay, so, but what Daniel teach you is very important. If you will calculate in the proportional wire counter, and you know how the charge is generated, so, and look for the total charge of the avalanche, which is produced as a small distance from the anode, then the electron and ion contribution to the induced signal can be actually calculated in this way. And for the counter, which is 10 micron diameter, etc., the electron induced signal is negligible. So what you collect, the signal on the wire through your electronics, corresponds only 1% to electron. All comes from the ion. And straw is a perfect single wire proportional chamber. Okay? So most of signal comes from ions. And I recall you that we get a better understanding which ions are drifting in the special. So you have to take this to account. Of course, if you would be rather just measuring the total signal, you will get something like this one. And this is a time. But of course, you don't want to collect all of the ion signal. It's very big, it's very lengthy, a new particle can come. So you basically, how to say, shape it or introduce electronic shape in the so-called RC high-pass filter with different time constant. And here how your signal from the multi-wire proportional chamber will look like depending from the RC high-pass filter, okay? So the total signal without electronic shaping would be dominant by ion. But what we are measuring in the chamber, we cut most of the ion signal. Clear. But we need to understand basic processes in the detector in order to simulate this. And Garfield allows to do many of the simulation. And then many of us in gaseous detector fields grow up on the book of Fabio Sauli in 97. It's some small book, Principle of Operation of Multi-Wire Proportional Drift Chamber. I give it to all the students which come, start with this book, read this book. It is really very nice and very educative. And particle detection with drift chamber, why I'm telling you, because here you can get a really very significant calculation if you want to go into the details of all the signal generation, how it is done. You can derive your formula yourself. This is much more advanced. But this is a basic and this is more advanced. But these two books very nicely shapes your understanding of the detector response and how it's going. Okay, now, single wire proportional chamber is clear. Coming back to the Nobel Prize discovery of Georges Charpak. So what you can do, instead of the single wire proportional chamber, you can put a set of wire at the equal distance in between the two cathodes and then apply the voltage. So you don't have a single wire, you have a multi-wire proportional chamber. This is what it's called. Then you apply the field, the particle travels, then the electron drifts to the wire, there is an avalanche here, electron is collected, and ions drift long time to the cathode. Yeah? So this is a basic idea. The high resolution of wire chamber with a limited readout, if you have a spacing of 1 millimeter, this would mean that if you only measure which wire particle is going through, your resolution would be limited to 1 millimeter divided by square root of 12, because it's a uniform distribution. You don't know where the particle passes, 300 micron. But there was another clever idea, which is used currently in LHC and cathode strip chamber. You can patent the cathodes in strips. So to collect ion charge, which is coming, okay, to the cathodes. And then if you pattern them in two directions, in terms of the strips, you can get by the center of gravity method another coordinate and improve your precision of 300 microns. It depends from the signal over noise ratio, but typically, thanks to the using both information from the wire and information from the pattern cathodes, you can get to special resolution of the order of 100 micron. This is, you should remember, I just point out, this is a typical resolution, more or less, between 50 and 100 micron, which you can get with from the wire type detector. You don't aim more. This is a limit because of diffusion, some other fundamental processes. You should remember, this is resolution which you have to keep in mind. Of course, you can ask, I have a distance between 1 millimeter between the wires, but I want to put them closer, then I have a better resolution. No, it doesn't work. Because here what comes, the small wire replacements reduce the field quality. And you need a high mechanical precision. Remember, these wires can be a few meters long, 4 or 5 meters long. They have a sagitta because of tension, they have a sagitta because of gravitation, and you destroy the electrostatic stability of the chamber. So basically, this is very important that, for example, that for the wire diameter, if you take it for 10 microns anode wire, then for the wire spacing of 1 millimeter, you have maximum stable and supported length of about few tenths of centimeter. Okay, beyond this, you might start to have a problem with electrical instability. Again, one of the important points, of course, you can try to calculate many things analytically, but better to use Garfield, because Garfield allows you to simulate collective movements of the wires and to consider all forces, for example, between anode wire and electrodes, gravitational force. This is actually what was introduced around 2010, which allows you much better than analytically evaluate these processes which is going on. And here you can see the first presentation of the multi-wire proportional chamber by George Sharpak, Nobel Prize winner in '68. And actually, if I'm correct, the first large experiment containing this chamber took place in the 70s, 80s, with 40 large area multi-wire proportional chamber at the CERN ICR, which you can see here, I installed. And then another important concept which was developed was the following. Before we discussed that we only measure the coordinate, which wire where the particle passed through. But in addition to this, what you can do is actually try to measure time of the arrival of the electrons to the wire. And this comes the concepts of the drift chamber. Actually, Atlas TRT and other experiments were utilizing. So what you basically do, the first electrons, so you have an electrons, but then you measure not only which wire, but also arrival time of the electron. And by knowing the time, you can correct it through the distance, the so-called RT relations, radius time relation, okay? And this is where, as we discussed, for example, this is one of the gas mixtures. This is a drift velocity as a function of the field. And for the hydrocarbon, noble gas hydrocarbon mixtures, you see the drift velocity is saturated. So basically it doesn't depend from the field. This is quite convenient because most of the time the electron drift in the uniform field. And then the non-uniform field starts here. So if you have a uniform field, it simplifies you the development RT relation. It is possible to do even without this, but this is how the first drift chamber were working because it brings you less systematics. But the key element, the key message I would like to bring, so you can measure the time, and through this, you can try to improve your spatial resolution. And basically, there are several things such as, primary ionization statistics, fluctuation, diffusion electron and gas, electronic noise, etc., etc. We were discussing a little bit, but this is all ingredients which affects you measurement of the coordinate. and then this is what allows you. But again, the typical drift chamber gives you special resolution of the order 50 to 100 micron. And there were many different chambers of different designs which were constructed and operated. Here you can see wire, but imagine this is all stretching each wire, fixing. It was a labor and time consuming job. I mean, there was a special facility in Siasakle where there was a wire chamber constructed for a long time. So it is really takes time to construct wire chamber. Okay, going further, I think as very nicely Daniel already described you, in the original LHC experiments before upgrades and before the new, the gaseous detector were mostly installed in muon tracking. We discussed this is where we need to cover the large area with a moderate resolution of 150 to 100 microns at a moderate cost. So this is what you do. There was not so many examples of gaseous detector in the inner tracker. The best one was TIFR. And you already heard how this detector was constructed. And actually, thanks, Daniel was a project leader of this project for a long time. And then he and his team, this project survived more than it was anticipated, which actually, usually it happens vice versa for gaseous detector. You build a detector and there is this agent problem, etc., comes earlier, and in this case. But you also had originally the straw tubes in the LHCb experiment and time projection chamber in multivariate proportional chamber. But you see clearly the domain of gaseous detectors is a muon tracking. Okay, and here you can see we discussed already the largest and the most modern time projection chamber is the LIS one. It has a length of 5 meters, diameter 5 meters, volume 88 square cubic meters, detector area on both end caps 30 square meters, and 500,000 of channel. And here you can see the construction and comparison with the past TPC and the future TPC, which is proposed on the linear collider. And I don't want to go in details. We already discussed the DPC has an advantage that, for example, in lepton-lepton heavy ion collision, it allows you track point recorded in 3D and particle identification of d over dx, because when particle goes through this volume, it produces on average, I mean, few hundred of the electron ion pairs. And as we discussed, by this 200, you can measure d over dx and provide particle discrimination. But it requires also very uniform electric field across drifting. And as we discussed, the B field, which is there, also allows this omega tau, if you remember still this suppression of the diffusion, which is extremely important. So, but it is not, cannot be installed in experiment Atlas and CMS. Why? Why it cannot be installed? Why? No, magnetic field exists in Atlas and CMS. Why you cannot install? Ions, the key word is ions. Space charge effects. If you have arrays every 25 nanoseconds, you produce electrons, which is drift here, but you also accumulate huge amount of ions, primary ions, not those who amplify here and you can remove somehow with some techniques, but you have so many ions in the space charge effect, which drifts you hundreds of microseconds, that everything would be destroyed. Your electric field would be distorted, space charge effect. Clear? So you can do it when you have a large particle multiplicity, but which happens via LIS, because they're studying ion-ion collision. So it's a huge particle multiplicity, but rare. And if you have collisions like in Atlas and CMS every 25 nanoseconds, which huge number, this volume would be spoiled within the microseconds, milliseconds, okay? Clear. Good. Okay. And then I put on the slides still Atlas TRT. I don't need to take. This is fantastic detector based on wire chamber technology, was explained today by Daniel. And also in the muon detector of the CMS, you have the so-called cathode strip chamber. And remember, the idea which I was telling about Fabio Sauli and George Sharpak about segmenting cathode into the strips, right? So you can get, if you put a spatially closed wires and segment your cathode into the strips, you can get additional coordinates and again, get a resolution of the order of 100 micron. Again, this is a number which should stay in your line. The typical resolution of gaseous detector wire type things is order of 100 micron. You can improve it a little bit, but this is what you should bring from this lecture. There is another concept, which is actually some of you were developing or develop in India related to the resistive plate chamber. This is a very nice device to actually provide. So basically it consists of two resistive electrodes. So in this case, multiplication happens not around the thin wire, but in a parallel plate geometry. This is clear electrostatic how the charges, but you have a resistive electrodes. Why? Because you put a lot of them high voltage, and then when particle is passing, it provides a single electron ion pair. They start to drift, and this induces the charge, but then resistive electrodes allows you to quench the charge. Okay, so you don't go to spark, but it somehow goes into the limited streamer mode or avalanche mode, depending on high voltage you apply and you register. Why it is good? Because it is simple device and allows you to provide a trigger. So whenever muon comes, for example, through it provides you the bunch crossing trigger within the 25 nanoseconds. Usually they have a time performance of 1 to 5 nanosecond. Okay, but of course it is tricky because the choice of resistive material, quality, effects, dark current rate, etc. So this is not so straightforward. So this is another detector, but it's used in all of the experiments. But your rate capability is not great because it's defined by your resistivity. This is clear. Okay, and then the last example of the drift chamber, it's a multi-wire drift tubes. It's pretty much the straws, except of the material. In this case, the cathode done not from straw, from aluminum, but again, the single wire. And I think this is detector which is installed in Atlas, sorry, it's Atlas muon drift tubes, shows you an example. Here you can see the special resolution as a function of drift distance. The total length of the straw is 15 centimeters. And here you can see how the special resolution based on RT relation, you remember, will look like without rates. And here, how it will look like due to the due earth rate 1 kilohertz per centimeter square. And you can see the special resolution significantly degrades, both when the particle crosses closer to the wire and higher to the wire. Why? Because when the particle closes close to the wire and the rate increases, the ions is not able to accumulate. So you create around the wire from the previous avalanche. The previous avalanche still remains over there. So your electric field is distorted around the wire, okay? So, and this brings you the issues in URT relation, degrades it. And also at the larger radius, because the ion need to move up to the cathode, and it takes a time. And while they're traveling, they're also distorting electric fields. They're distorting electric field, they distorted T relations, you have an issue. Okay? So this is a two major limitation which actually lead to the development of the new micro-pattern gas detector. The original idea was to develop detector with a special resolution between those wire chamber and silicon pixel system for tracking. And actually, as Daniel was pointing out, they were also developed for the CMS. But then the original concept which was developed for CMS, it failed. And the advantage was so somehow to try to think about the technology which allows you the better wire spacing. The better wire spacing means better rate capability, more particles through, and reduce the cell size using the chemical etching of photolithography technology. At the end of the 90s, you can start to use photolithography technology. And this was the advent of the so-called new micro-pattern gaseous detector. So the idea of the first detector, which appeared not very successful, was just to replace the wire, which is produced at a distance 1 centimeter, by photolithography, print cathode strips, anode strips, okay? With a typical distance, you can do this 100 micron. Here you have a 1 centimeter, and here you have 100 microns. And then the mechanism, the particle passes charges through, you apply voltage here, and then you ionize it and collect it. And of course, since you have a much shorter distance between anode and cathode, you can evacuate ions much more quickly. Clear? Ions removes from the volume much more quickly. And by this, you improve the rate capability. Here you can see the relative gain drop as a function of the rate for the multivia proportional chamber and for the microstrip gas chamber, which was invented by Anton Oed in 98. And you see, you can increase 10 to the 5 particles per millimeter square, 10 to the 7 particles per millimeter square. You can increase significantly the rate capability of your detector. So you replace wire with the strips. Okay? And but the problem appeared of the structure of this device itself, because here you can see the 3 major plots which is used. One of them is the detector efficiency, so basically your efficiency to detect MIP. This plot is a gas gain, and then this is a discharge probability when you expose not to electrons, not to X-rays, but alpha particles. Alpha particles is different by what? Their primary ionization is order of magnitude more than MIP. If MIP produces at 1 centimeter 10 electrons, alpha particle produce 10 to the 5, okay? So dependent. And then you multiply by 10 to the 4 gain. And here appeared to be an issue. So discharge probability when you constructed the first these detectors, in principle, in presence of alpha particles, is an intrinsic problem. Why? Because of one of the important points. So here you can see the microstrip gas chamber, and then you, for example, switch on this gas chamber together with alpha particles. You will see that your structure, because it was a fine peak structure of the electrodes, which is usually created from gold, micro discharges spatter you part of this structure. But this is detector still works. But then comes another discharge, which basically can shorten you the electrodes, and your chamber start to work. And this type of discharge, it's like lightning, okay? So the typical time development is very fast. It's less than nanoseconds. You cannot just shape by the electronic and protect your detectors. It doesn't work. And it comes from one of the fundamental equations which exists in theory in gaseous detector. You have a so-called Rather limit, which is says the following: whenever your avalanche reaches 10 to the 7, 10 to the 8 electrons in the avalanche, you go to spark, okay? So, and then this problem which came from the point that since your primary ionization, you need to adjust your gas gain in order to detect 100 electrons, okay? 100 electrons, you select for electronics, gas gain 10 to the 4, 10 to the 6. But if alpha particle comes, 10 to the 5, primary 10 to the 4 gain, 10 to the 9. So it is unavoidable that in case of alpha particle, you will get a discharge whenever it comes. So basically, you cannot avoid sparking in gas detector. You need to protect your electrodes so that they're able to work whenever the avalanche comes, okay? And this was a problem with the MHGC, so it appeared to be too sensitive to the effects which is related to the sparking. And this was original concept which was proposed for the MHGC detectors. And actually there was a telescope of 32 MHGC detectors tested in the PSI in Switzerland, and this was one of the CMS milestone. But then the CMS experiment decided to move to another technology, the all silicon option. But it was used in a couple of experiments in carabiner tracker and some other things. But of course, it was not reliable enough. It was good for measuring MIPS, but not for the LHC type of experiments where you could have alpha particles basically in many collisions. I think you're a little bit tired. Questions? Everything is clear. What is not clear? From here is better to hear the questions. No questions. You're saturated. Like not in proportional mode, you don't acquire information according to amount it comes, you're in saturated mode. So you reach your saturation for today. Yes.
Yeah, so when do we use streamer mode and when we use avalanche mode in RPCs?
Well, it's better to use avalanche. The streamer mode was originally used because of electronics, larger charge, you need a less sensitive and cheaper electronics. Otherwise, because of these radicals and age information, you try to work gaseous detector at the minimal possible gain you want. As soon as you overcome the threshold, it's very practical from this point of view. The less noisy electronics, the more expensive it is. So it's sometimes also. More questions? Yes.
That we use in RPC. So how do we decide upon that?
Good question. You need a mixture which provides you, usually why we use noble gases as a major element, because it allows you the avalanche development at the minimal high voltage. Okay, so this is why you can do with CO2, but then your detector would need to be biased not with 2 kilovolts, but with 10 kilovolts. And then the problem comes from the mechanical construction, not about the discharge in the gas, but it's sometimes discharge in the surfaces. For RPC, you always usually use some of the gases, noble gases, but since in RPC, you apply very big high voltage of the resistive electrode, you need a gases who is quenching and who has some sort of the electronegativity as well, like SF6, to stop. So you basically select the gas based on the idea to quench effectively discharge and doesn't allow you to propagate transversely, because in this case, you will lose also spatial and time coordinate. And now the key element, all of these gases is not green-free. This comes a problem because many of these gases with quenches, they have a very big global potential and they might be forbidden to use at CERN very soon. So now there is a dedicated effort to try to find the green friendly gases. And this effort for the time being not successful because you cannot easily find green-free replacements because of other reasons, aging, toxicity. So it is not so straightforward to replace it. Okay, let's go further. Aging phenomena is already pointed out by Daniel to you. So basically you break quencher molecules. And then this polymerization, whenever you break these molecules, many of them has a large dipole moment. So they can easily combine to each other, have found a more heavy component, and because of electrode dipole moment being attached to anode onto the cathode. And this is what you have. You have on the perfect electric, some dielectric, which modifies the field, and then basically you changes your wire operation. And there was a first workshop in '86 where the things were started still the black magic. Then there was another workshop in 2001 where already the things were addressing in terms of the operation of gaseous detector at high rate, and in particular FEB experiment where Daniel was one of our referees. We were reporting to him how our detector failed after being exposed few days in the environment, because environment of the FEB experiment for the particle rate and were quite comparable to the large to tracking in large.
I heard few hours.
Sorry?
Therapy, I heard I think
few hours, then few other prototypes, few days, but then we develop. But again, I mean, this is what comes what I could consider causal design, because the problem was related to the conductivity of the cathode surfaces. So the ions were not neutralizing, and solution which you found, you have to cover honeycomb all the cathodes with gold layer. So this is a price to pay which you come to increase the conductivity. So you basically were doing the things. So this is one of the points, but still, I mean, many things which were discussed at the FEB was systematically addressing aging phenomena, and then it was followed by all of the experiments. And here you can see how can your wires look like. This is what Daniel was showing here, for example, on the microstrip chamber, some bubbles. This is a pictures from this 2001 workshop. And actually, there would be another workshop this November. So basically, it's every 20 years we discuss about aging, about the personal experience in aging as well. And this is actually would be another third workshop in series, which will be organized this November. But in all cases, so we discussed MHGC, unfortunately, microstrip gas chamber was not successful because the structure was very vulnerable to spark, to aging effects. But there is new concepts which were developed and which actually become much more robust and stable, such as micromegas, gas electron multiplier, and another concept, and here you can see. And again, these concepts also provide you greatly increased rate capability because it's done by the same technique of photolithography with a structure which is much, much finer than via chamber, the typical distance in 100 micron. So one of them is a gas electron multiplier. So you have a 50 micron of copper, 5 micron of copper on both sides, and then you apply electric field between the two sides of this chamber, okay? So, and then if the electron comes, the avalanche happens within the hole. So somehow it is some sort of the not multi-wire chamber, but multi-hole chamber, okay? But the typical distance between electrodes and 100 microns, it's not 1 millimeter. So your rate capability is greatly increased and your spatial resolution is much better. And then extracting the electrons, you can get the signal on the readout board, which is placed few millimeters from the gem at any, any form, any shape, whatever you can imagine. And here you can see the simulation. So basically, the electrons very quickly, and then the ions, you see? So the electron comes, it generates avalanche. The electrons very quickly goes down, and then some of the ions is absorbed on the upper part of the gem holes, and some of them goes here. In order to avoid discharges, you can assemble detector which consists from several gems, gem 1, gem 2, gem 3, and just share the gas gain between these few factors, reaching the total gain of 10,000 between the three stages. And then you can, amplification happens in gem, and readout and collection happens on the pattern electrode board of any size, and you can see any readout structure as you want. So, and this detector, 3 gems or 4 gems, what is used for CMS experiment or for the least time projection chamber. Another example is micromegas. There will be sound now to wake you up if it happens. No, usually it is. So basically you have a PCB, and then on a pillars of 50 microns, you put a mesh, and if the particle comes, it produces your primary ionization, which drifts towards the mesh, which is 50 micron distance, and then these electrons multiply in the parallel plate geometry of only 50 micron and being collected on the strips. And this is actually how it happens. So you collect the charge. It's also somehow micro-pattern gas detector you collect, but the difference to the MSGC, you don't have anode and cathode position. So this detector is vulnerable to the discharges, but discharges doesn't kill the very fragile anode electrode structure. Here you have only PCB and the field applied not from anode to cathode here, but from the mesh to here. So this is another concept which is used in the Atlas new Smallville upgrade now, which is very well developed. And another point is related to the simulation and modeling of the MPGD, because we discussed about simulation of the wire chamber, but with MPGD, micro-pattern gas detector like GEM and Micromega, there is a very big difference. Because you really need to utilize everything what is in the microscopic tracking. Because the mean free pass of electrons in the typical gas like argon is approximately 2 to 3 microns. And the typical structure of the micro-pattern gas detector, this is few tenths of microns. We discussed GEM, 50 micron, hole, distance, etc., etc. So the mean free pass of electrons approaches the structural elements. So you really need very carefully to track electrons on the microscopic level by transport equations in order to get, for example, properly the gem charging up effects, where, for example, some charges goes onto the electronics, or, for example, some mesh transparency in case of Micromega. So this is what is related to these points. And last but not least, there is, I mentioned you about the concept of micromegas, okay? So it's basically what you have readout board, then pillars, and then the mesh at distance of 50 microns. So this is how it is positioned in this case. But the idea from the beginning of 2000s approximately was, why don't we try to put the mesh by means of the advanced CMOS post-processing technology, the silicon technology, not just mesh on pillars, but you take a silicon pixel chip, And then you take post-processing technique, which is widely developed on silicon, and you put the same mesh at a distance of 50 microns on top of the CMOS chip. So you basically have two detectors in one, because on top the particle passes and produces your primary ionization, electron diffuse, you produce avalanche here, but then the charge is collected directly on the fully integrated CMOS silicon chips. And then automatically you have a full processing in the underlying levels of CMOS technology. Of course, you need to protect this chip, and usually you take a CMOS chip and you put a few microns of the silicon nitride or any other things in order to put a resistive layer. So your spark does not destroy exactly the chip. It's sometimes successful, sometimes not, but you can do two detectors in one. This is just to keep you in mind. So there is a concept which is being developed to integrate gaseous and silicon detector in one device. Okay? Very good. And then I think this comes to the summary of, I think the advent of the micropattern gas detector, which were invented in the beginning of 2000, was not rapid as was originally. I told you the MHGC story was not success. And before the community get a trust that GEM micromegas can work, it took some time. But it was clear that because of the need to provide the finest special resolution, about 2010, the people started to talk that we need to exploit more for the upgrades of LHC experiments, this technology. And here you can see the table which actually shows you the MPGT technology in the CERN experiments. And actually, as you know, that all major experiments develop the upgrades for the Atlas, CMS, ALICE, and Compass detector based on MPGT technology. The Atlas new small wheel, which was constructed, uses micromega detectors. The GEMS is being installed, triple GEM detector being installed stations in Atlas GEM, and also multi-wire proportional chamber and ALICE experiment were replaced with GEM detector. And also more robust structures were developed for Compass Ridge. And for those who is really interested in the technology, last year, all these upgrades were successfully completed. And there was a 3 big detector seminars at CERN about Atlas Micromegas, ALICE, GEM, and GEM detector and CMS. So I would refer you to Indico slides and those of you who is interested to get more insights from these detectors. And I just put these slides not to tell you because it's very technical one, but it gives you some of the major points which were encountered during the upgrade of micromegas of Atlas new small wheel, GEM for CMS, muon system. It's some technology issues. I just keep it in the slides for those who would be interested. And also for the development of the TPC with the readout for GEM structure even for the ALICE in order to meet the requirement of the energy resolution. Again, and also the TPC is proposed for the future international linear collider, which would be E+ and minus collider. We already discussed with you that TPC is well suited for those applications, which is lepton colliders or electron ion colliders. Okay, and there is a lot of the dissemination of the MPGT technology for nuclear physics, for neutron detection, for photon detection, even for cultural heritage. I would say, for example, understanding the void in the pyramids, you can assemble, there was a test assembled mini detectors and you can study the structure. So basically, there is a lot of the opportunities beyond colliders, beyond LHC, which comes to different applications. So this is why they're not only used for particle physics. And now in the last 5 to 10 minutes, just a few words about technology trends. So of course, we already assembled the detector for LHC upgrades. They're widely used for nuclear, for particle physics experiments, colliders. So let's go back now from the big projects to the basic science as well. So what are the trends which can be interesting to people? And one of them. One of them, as we discussed, all single-stage micropattern gas detectors, they are prone to discharges. Rather, theorem, you cannot squeeze out anyhow. It would be discharged. Of course, in micromegas, Discharge is not destructive the structure, but in this case, you need to protect electronics, and any discharge generates you some dead time. So detector is functional, but the dead time comes from the electronic because you need the protection. What is also more important, we were discussing in wire chamber, the signal is generated by ions. In micromegas, the signal generated by ions, yeah, because again, ions moves towards the cathode. In gem detectors, the signal generated by electrons only, okay? Because it's electrons which arrive to the readout electrode. So this is also very important when you consider different consideration, how to select gas mixture, which detector is there. But if taking micromegas, and if taking other microstructure gas devices, I didn't want to spoil you with different geometry, but the basic idea is the same. You put by photolithography very fine pitch structure at the order of 100 microns, okay, 50 micron, 100 micron, etc. And this is why, since all of the devices is prone to discharges, so what you do, you consider depositing on the micromegas resistive layer. Somehow you're going out from fully electrical detector. So you introduce dielectric, but this dielectric strips, for example, allows you to quench the discharge. And by this improve characteristic of the detector. Yeah, you can argue we can introduce some new material and can lead with aging, etc. This is a different topic of discussion. But this is one of the trends. So you basically try to introduce resistive materials and make the detector half resistive, let's say, like this one. And there is a lot of the interesting development related to the new processing machines, diamond-like carbon resistive layers, where you can select your resistivity, because your resistivity, the higher resistivity, the lower your rate capability. You see your rates. Another question, as we discussed, usually the gaseous detector were considered that they give you time resolution of order nanoseconds. And nobody ever thought that you can get to picosecond regime. And now there is a project where you can measure the precise timing with a picosecond regime. It's probably not yet up to the levels that you can build the big detector, but there is a very promising R&D ongoing. Another question, which is related optical readout. We were discussing with you before only that we collect the charge, but in the avalanches, you produce photons, a lot of photons, even more than the charge, right? Because avalanche produces you both. And then why don't we register the photons, which is produced in the avalanche? You can register charge and photons, or you can register only photons. And this is optical readout. And then interesting point, for example, what you also try to merge or make a marriage between MPGD and some of the innovative components like graphene layers. And I think one of the points which is very important, as I already was discussing you, is the development towards picosecond timing, because you know all of the LHC upgrades now understood the importance of picosecond timing. You would be having lectures because it allows you precise particle identification and association of different track to different vertices. Because as Daniel was explaining you, the vertices can be many vertices in collision. And for the high luminosity LHC upgrade, you need a picosecond timing to improve your resolution of your tracks corresponding to different vertices. And two of these developments is related. One of them is creating the so-called time of life detector based on many RPCs. If you make like 20 layers of RPC, but take off one of the signal, you can go to the picosecond timing. And by using study with the new materials, low resistivity gas, you can try to go down to 30, 40 picoseconds. And another question, which is related to using timing resolution in micropattern gas detector, when you take a micromega, which we were discussing, put the cesium iodide photocathode or more robust photocathode, and then particle which comes, creates you many photons, because you cannot reach with a single electron nanosecond resolution. You need to create many and then remove your statistical fluctuation, improve time and resolution with its scales one divided by square root of n, okay? And the prototypes of making such a detector with a micromegas photocathodes also ongoing. There is a lot of things which is related. So this is one of the timing. Think about timing. This is interesting development. Optical readout. So whenever you have multiplication in gem and micromega structure, you can try with the cameras, high resolution camera, to get a light. And you can do many interesting measurements for radiography, for energy resolving images. Here you can see the helicopter. You can even do these things in real time. And these all images, which is received not with charge. So you basically put your beam, then you put your object, you put detector, and then you do your imaging, result imaging in the optical readout. So it brings positive, but it's a very interesting development from many things. And last but not least, what was also considered is using the graphene-based detector. So you deposit, for example, graphene on top of gem and try to change the permittivity of the gem for electron ions modify. So you try to make a marriage between the graphene and gem detector. So there was original things which we are discussing. Yes, I am continuing. And the last two slides, which I wanted to tell you, I know that you are very tired. I know that you are fully saturated if you are not in Geiger mode, but I put a lot of slides for you trying to motivate you to look this in more details. And as Albert Einstein was saying, knowledge is limited, whereas the imagination embraces the entire world. And what we are as a scientist, what it gives us a possibility to bridge a gap between the science and society. And the role of the big high energy laboratory like CERN, this is innovate, discover, publish, and share. And in order to bring the world a little bit closer together, and this is what we are today here. Thank you very much. Now questions, I go here because otherwise I cannot hear questions over there.
So my question is, when do we use flowing gas in the detectors, and when can we just put a gas in a detector and let it flow, let it be there?
You should better use always the flowing gas. So you see, it is only the question if you want, for example, it depends from application. If you send a satellite, you unfortunately cannot send a recovery satellite. So in this case, you need, in principle, the characteristic of gaseous detector degrade with the time. Because, I mean, as we discussed, the quencher amount being used, utilized, some of the project can accumulate on the anode, bias, and cathode. So it's better to sweep out the detector of gas all the time. So whenever you have, do it. Of course, if you make a satellite mission when the gaseous detector send, then you don't have this possibility. You can recirculate, but you cannot add new gas. You must do this. Also, why the gaseous detector, how to say, did not find so much how to say, distribution within the medical imaging, because the doctor doesn't want open close bottles. They want usually the program, so they press one button and they get everything in the image. They don't want to do this. But there was a lot of the developments in the medical field when, for example, research institutes were working together with hospitals, and then scientists were helping to share and actually to do some medical imaging with gaseous detector. It was successful, but it was successful to the extent that it can work if there is an interest from scientists and doctors, but to make a commercial product for Siemens, they would only need to make a detector with a filled with a gas. And then it's a question how many it survives. It depends from the dose rate. So the rule of thumb, flush it. In case you cannot, think how to make it as long as possible, but there is no general recommendation in this case.
All kind of quenchers dissociate. Me like if we get CO2, it's a very stable molecule.
All type of quenchers dissociate. The CO2 will not produce your aging effects, but as Daniel was telling you, your detector pollutions like silicon in the gases can also accumulate on your wires, and get rid of silicon, it is nearly impossible, even if you do everything. So the pollutions can give you the things which actually load gas in from the things. So it's always better to do the things. But again, in some of the cases, like space mission, you can do this. But in the collider experiment, more questions? Yes.
Yeah. So my one question is that what is the radiation damage of these devices, gaseous detectors?
With
Radiation damage of say RPC or micro chambers, this micro pattern chambers. What is this radiation damage of these devices?
Well, the radiation damage of these devices, this is what I would partially agree with Daniel. It's a chemistry, but it's a black magic. So usually, in case the MSGC, as we discussed, wire chamber has this rule of thumb, the Atlas TRT survived probably at the limit of what is possible for wire chambers. MSGC is much more prone to discharges than wire chamber. MPGD shows a high radiation resistance, but there is one major issue. If in case of silicon, you can quantify everything by the total dose of accumulated charge, here depends a lot from the construction material, cleanliness of your system, etc., etc. This is what Atlas TRT passed a very, very big way through in order to build the detector. So one minor mistake, you did not check here, you did not check some connectors with the silicon, and the detector radiation hardness can be significantly smaller. So somehow building the red hat detectors, this is a chemistry, but it's a black magic in terms that you cannot afford any single mistake to happen. Now, with the micropattern gas detector, for the time being, especially you introducing these electrodes because, how to say, you can speculate once the MPGD seems to be more, how to say, stable than wire chamber. Maybe because the field which is generated for the amplification is smaller by factor 2-3. Maybe because the electrode structure like micromega already contains some resistive elements. So basically, if you have a parallel plate structure, so even if you deposit something, your gain doesn't change as much. But for the time being, the experience, there was no major failure with the MPGD, except silicon pollution were seen. Whenever you don't control silicon, you get aging also in MPGD. But somehow, from the current point of view, it seems harder. But again, the limit would be defined by cleanliness of your procedure and black magic and chemistry.
What about this FEB?
Well, FEB was using MSGC and wire chamber. At that time, there was no steel gem. Gem actually was added to the MSGC like pre-amplification stage because MSGC itself was suffering from discharges, detectors were destroyed, and then Fabio Sauli proposed, let's put a gem and do two-stage multiplication and not like 3 gems, but because we already built MSGC chamber. And this is a little bit allowed to decrease the sparking rate, but it didn't solve the problem conceptually.
What are the advantages of the straw tubes respect of a drift chamber?
Sorry?
Drift tubes, tubes respect of the drift chambers, the working principle seems to be the same, but what are the advantages to use tubes? So to contain the gas just in a small volume around the wire.
Well, first of all, it's a question I can also give an answer. An expert from TRT, there are a couple of things. So first of all, you have the question is evacuation of ions, the key elements, okay? So you want to make a small distance between anode and cathode wire. And also with straw tubes, you have a smaller material. It depends the structure, because you see in case of TRT, there is also these straw tubes in between other materials which produces your TRT photons. So it depends more on the structure of your chamber. If you just want to cover large areas, you use drift tubes, but then you're limited by the distance anode to cathode. In this case, you try to make a straw tubes with a minimal amount of material. It's a straw, so it's a thin, it's a tenth of microns of the thing, so you minimize the material. And then in addition to this, always, or another important consideration that it is always when you do the straw tubes or single wire chambers, you know how your gas flow goes. This is a problem for the big volume chamber because simulation of the gas flow, it was not so straightforward. It's a hydrodynamics. When we were building the first detectors, you know, big ones, you know how we were testing how the gas goes out of the chamber? I tell you, smoking inside the chamber. And then you say, try to smoke in the corners of the gas, and the people trying to smoke and the gas never goes to the corner. So for example, understanding the hydrodynamics, take a cigarette, and if the chamber is transparent, you do it, you smoke in the chamber, you understand. Of course, you can simulate it, but it is also because the gas flow, as we discussed, flow is extremely important. So somehow to remove the things. And if you leave some corners of the chamber without the proper gas circulation, which, for example, in a big drift chamber, You need to think not how the gas goes in out, but how your cornices flush, because this is where your agent can start. I leave the floor to argue to Daniel why TRT was the best detector. Yes.
Hello, thank you for such wonderful lectures. My question is, in time reaction chamber, we use electric field and magnetic field parallelly, so the diffusion is less.
Yes.
And
Transverse.
Transversation. And if we make a time reaction chamber without magnetic field, so there will be diffusion, and we'll get some track which is diffused.
Well, I didn't tell you the whole story. Magnetic field we need for momentum
Yeah,
reconstruction.
that is also true.
So you see, if you use only electric fields, then you use the basic point, you cannot reconstruct momentum. So it's a combination of both, because it's not every gas which, for example, changes your omega tau. It is dependent from the fraction. I showed you argon CH4, which was given. There is another gas which gives omega tau the factor of 20. It's CF4 related. But again, this is equation. So you somehow do two things. You improve spatial resolution. But of course, the time projection chamber without magnetic field doesn't make sense. You cannot measure momentum of the particle. You're not tracking detector.
If we want to measure low energy particles which doesn't go very far, or like high Z particles which give tracks of few centimeters, so the diffusion will be more if we don't use any magnetic field. And can that be calculated by hydrodynamic equations? If we get a diffuse tracks,
Yes.
the original track and the diffuse track we are getting while drifting the electron through the drift volume. So if we calculate that in maths, is it a good approximation if we get a diffuse track? So that we want to know the original length of the track made by some charged particle, let's say by alpha particle or something like that.
Well, I mean, it depends from your, it depends, we need to discuss. I want to try to understand what you exactly mean, because you see the different tracks is better, what I was trying to tell you, the analytical expressions, the simulation methods develop very strongly during the last 20 years. And it's really do a microscopic tracking. This is what I try to do. So you basically track every 100 microns, all the processes, reactions. Analytical calculation, like what I was showing you, good, just to have a feeling. But if you want a precision, don't do any analytical calculation. Even for wire construction now with a Garfield, you can do precisely, because they're all good, but not so good. And coming back to your diffusion things, I mean, it depends also from your momentum of the particle. Remember that the small energy tracks, like 100 MeV particles, they would go like this one. Okay, and this is what you need to disentangle with the high PT tracks, which gives you a momentum. So it depends exactly what you are going, what you want to do, and how you want to disentangle the things.
Let's thank Maksym who came in for a beautiful talk.
Yeah. Yeah, and last question before, I just wanted to say the lectures are uploaded. I am here until tomorrow. So basically, if you want to discuss something, you grab me and you look the things and you try to ask your questions. And if something, send me mail asking the question.
Now, I will take 2 more minutes from you. So thanks, Maksym, for your excellent talks. And we try to keep the JM micro-mega proportional chamber and RPC4 in this experiment. But some reason JM is not there. Other 3 experiments are there. Okay, and then this one more thing, you may see these pictures in the behind everybody. I'm saying our founder director, he was a very fond of this art collection, and he is himself as an artist. And this is this pictures one in the discussion with this Niels Bohr. There was the discussion table they were discussing. At that table, he draw these pictures. And so our institute has a large art collections, mainly because of him, and we collect. And from the behalf of the institute, I want to give these to Maksym. These are our art collections.
Thank you so much. Thank you. Thank you.
Yeah.
Thank you very much. I am really very delighted by this present. This is magnificent. So thank you so much. Thank you.
This is one small collections of the just local people paintings.
Ooh.
Yeah, that's
Fantastic. Thank you so much. Thank you very much for this wonderful present. It was a pleasure to give lectures, and as I say, grab me for any questions. I know you're saturated, but it will come with the time. Don't worry.
And
Thank you. Thank you, Gurjita.
it has a comment I'll give you.
Okay.
It has a comment. Okay. Just one thing again now, like yesterday, we'll stop here and after lunch, you will go for the defined experiment. Like yesterday, you come here, we'll take you the experiments and come back at 6 o'clock here for the another excellent talks, which will talk about that. That will not this, all this complicated. This is just in history of Indian high energy physics. So you come back by 6 o'clock.
Thank you very much. This is amazing.